Good day. I will do an electrodynamics problem known as rotating charge systems. So that's the title of the problem. And basically it develops the framework for how to do multipole radiation for a rotating charge system. Okay, so the text of the problem goes as follows. A common textbook example of a radiating system is a configuration of charges fixed relative to each other, but in rotation. The charge density is obviously a function of time. So charge density is a function of time, but it is not of the form that we would use in the usual derivation. Okay, so the charge density is not of this usual form. Okay, so how do we tackle a radiation problem in which there's a rotating set of charges? Okay, so show that for a rotating charges, one alternative is to calculate the real time dependent moments. That's part A of the problem. Okay, so calculate the real time dependent moments. Okay, and this is the real is a keyword here. Okay, and so calculate this using rho xt, but we're going to have to specify rho xt, and then directly compute the multiple moments for a given harmonic frequency with the convention of 1 by inspection or Fourier decomposition of the time dependent moments. Okay, and we have to, but basically what we also have to do is establish how to take the real part. Okay, and we have to do that with care according to the suggestion of the text of the problem. Okay, so first of all, let us specify a charge density which describes a rotating charge system. Okay, so what is a rotating charge system? Suppose this is my axis and I have some charges at particular positions. Okay, something like this, and these guys are rotating, okay, but they're rigid compared to each other. So they all rotate at the same same angular velocity or frequency. Okay, so charges are fixed relative to each other. That's important, and they're rotating at the same angular velocity. So in this case, we can write a time-dependent charge density as rho r theta phi minus omega 0 t. Okay, so that's our charge density. And now the first step is to write the time-dependent moment associated with this charge density, which has the generic formula r prime squared dr prime sine theta prime d theta prime d phi prime. That's just the volume element. And then we have r prime to the L, y L m star usually, theta prime phi prime, and then we have the charge density. Okay, so this is actually a triple integral, and the charge density is rho r prime theta prime phi prime minus omega 0 t. Okay, the first step is to shift phi prime. Okay, so we're going to shift the variable phi prime. Okay, so this expression becomes again a triple integral. So I have to write all this again, rho prime r prime squared dr prime sine theta prime d theta prime d phi prime, and then I will have again r prime L, and then I'm going to have, since I shifted phi prime, I'm going to have here phi prime plus omega 0 t, and then the charge density, but the charge density is going to be, in this case, time independent. Okay, so it's kind of like having the coordinate system rotate rather than the charge density itself. Okay, so I shifted phi prime, so the time-dependent part no longer appears in the argument of the charge density. It appears instead in the spherical harmonic. And why is that advantageous? The reason that's advantageous because we know that a spherical harmonic has a particular phi dependence. Okay, so we could write our spherical harmonic. It has some factors out front, which I didn't write explicitly, but they're just numbers. They're just factorials and pi's and other integers and a square root, actually. But here, the important thing is that here we're going to have an e to the im phi. Okay, so the dependence, the phi dependence of the spherical harmonic goes as e to the im phi. That's important. Okay, so according to this, we can rewrite our time-dependent moment as integral r prime squared dr prime sine theta prime d theta prime d phi prime. That's just the volume element. And then r prime l y l m theta prime phi prime. And then I will write here the charge density, which is rho r prime theta prime phi prime. And all of this multiplied by an exponential, sorry, this is actually complex conjugate, the way I've taken it, minus I omega, minus I m omega 0 t. Okay, so all the time dependence is in here, and we can actually bring this out in front of the integral, and we can write this in a much simpler form, which is the time independent multipole moment times a frequency dependent term. Okay, so this is actually our first result here. This is going to help us settle the overall question of how to calculate the radiation properties of a rotating charge system. Okay, so the important thing here is e to the minus im omega 0 t takes care of the time dependence, Okay, now this is a complex moment, okay, and we want to take real parts. Okay, so we're going to try to take the real part of this. Sometimes that is needed if you want just to calculate the moment itself. But recall that in the actual expression of a potential, you have another spherical harmonic. Okay, so I will show you why that happens. In that case, you don't just take the real part of this. You take the real part of whatever it's multiplied by. But before going there, let us do a little bit of analysis of how would we make this a real number. Okay, so and basically what the story boils down to, is that QLM, its definition includes a spherical harmonic, right? So here's our spherical harmonic inside QLM, and we know that if there's one identity that I'm going to use for spherical harmonics, which is that if you switch the sign of m in a spherical harmonic, it has this particular relation with the unswitched sign, which with YLM. Okay, so YLM is equal to minus 1 to the m YL minus m complex conjugate. Okay, so and for example, you can write QLM as in 3 parts if you want. You can write well, you can just write QLM 0 e to the minus im omega 0 t if m is greater than 0. For m equals 0, it's just going to be QL0 0. And an important fact about this is that this one does not radiate. Okay, so this is the m equals 0 term. It doesn't radiate. But the other thing you can do is if m is smaller than 0, you can relate it to the positive m part as follows. So you can write minus 1 to the m, and you can write here QL. Well, if so basically what I'm going to do is QLM, I'm going to use this. So QLM T is equal to minus 1 to the m QL minus m 0 QL minus m 0 complex conjugate, and that's also multiplied by e to the minus I m omega 0 t. Okay, but what I can actually write here is that for m smaller than 0, this is QLM absolute value 0 and complex conjugate. And here I will write e to the I absolute value m omega 0 t. Okay, and this is consistent with this. This is consistent with this. Okay, so that's one way to write the QLMT multiple moments. Okay, so this is an absolute value of m, in case it's hard to see. Okay, now, but the second important thing is that now let us actually delve into a little bit into what a potential looks like. Okay, so you know that basically a potential. So let me actually just consider. Potential is going to be something of the form rho x prime, and I'm skipping the time-dependent parts here, but each one of these is a time-dependent mode. Okay, so rho x, like I guess I can write rho x prime t prime here, or on the way, and x minus x prime dx prime. Okay, but the important thing is that you're going to expand the 1 over x minus x prime part, and you can expand this as Lm 4 pi over 2L plus 1, r prime to the L, r to the L plus 1, YLM, let me write YLM omega, and YLM star omega prime. Okay, so that's a usual expansion for the Coulomb term. Okay, and what is obvious is that you're going to have, so basically this will give you a QLM. I didn't write a time dependence here, but if you make this time dependence, it's going to give you a QLMT, but it's going to be multiplied by, in the QLMT, these primed variables are of course integrated, okay, and it's going to be multiplied by YLM omega. Okay, so and what we need actually is to take the real part of such a monster. Okay, and it turns out that to take the real part of this, what you need to do, okay, is again use the identity for spherical harmonics when m switches sign, but you're going to use it twice, so the minus one will cancel. Okay, so what you're going to have is that this QLMT YLM omega is going to be, well, usual form, QLM 0 e to the minus im omega 0 t YLM omega if m is greater than 0. Okay, it's going to give you some non-radiating terms of QL 0 YL 0 omega if m is equal to 0. That doesn't radiate because it has no time dependence. On the other hand, for m less than 0, what it's going to give you is QL minus m 0 star e to the I m omega 0 t, and YL minus m complex conjugate. And this has the argument omega. Okay, so QL minus m star 0 e to the I m omega 0 t YL minus m omega. So it's basically the complex conjugate of the m positive, m greater than 0 term. And if you add these, it's sufficient to say that what this term will be represented as is 2 times the real part of QLM 0 e to the minus I m omega 0 t YLM omega. Okay, so that's for m greater than 0. And this time independent part, which you usually don't care about in radiation, if m, because it doesn't radiate, for m equals 0, and you don't need to worry about the m negative terms. Okay, so this is how you take the real part. And this factor of 2 is of course important because this accounts for the plus m and the minus m. Okay, at the same time, here it is obvious that different m terms radiate at the same frequencies. Okay, thank you very much. This is the first part of the problem.